Hello everyone, I want to think now about the fast Fourier transform. And okay, so what I will be doing is that I will start off with the discrete Fourier transform, and from there I will try to derive the fast Fourier transform. Now, I'm not really an expert in this. I don't specialize in signal processing. I do not specialize in the mathematics of a Fourier transform, but I try to do it all from scratch. Okay, which means that I'll try to rediscover basically, okay, the fast Fourier transform. Okay, so we can write the formula for discrete Fourier transform in this way. Okay, so I'm going to write it here. Well, Fk, okay, this is the Fourier coefficient, equals to summation. Okay, now suppose we have n samples, and it means that we start from 0 and the last index shall be n minus 1. Okay, we have this small letter f subscript n. So this is the original data point, okay, and this is the Fourier data, okay, Fourier point I mean. Alright, so we have this exponent and to the power of minus 2 pi, and I, where I is the complex number, and we have n, okay, which is this, k divided by the big letter n. Okay, so this is the discrete Fourier transform. This is the form of it. Now the question is, how do we evaluate this summation? Okay, this is a summation, and we're going to sum up terms that looks like this. Okay, f and okay, this fn. So this is a scalar value. We assume a scalar input, data input, and this is the exponent. So how do we evaluate this? Now the best way to see this, I think, is that we try out some simple examples. All right. So for example, okay, we let n be equals to 4. No, we don't have to do with big numbers. Just let n be equals to 4 and see how we can expand this summation. And from there, maybe we can see some patterns. And from these patterns, we can derive faster way of doing a discrete Fourier transform. Right. So if n is equals to 4, then it means that we have this fk equals to summation 3 n equals to 0 fn e minus 2 pi I n k over 4, right? So the big letter n now has the value of 4. Right, but before I go further, okay, let me be clear on the meaning of this k. So k is the index for the Fourier coefficient, and k, it has a value ranging from 0 all the way to n minus 1. Okay, it's just like this small letter n. Okay, so it has got the same range. Okay, we have this, and assuming that n, the big letter n, is equals to 4, then we have this summation, okay, from n equals to 0 all the way to n equals to 3. Right, now what is the simplest way of evaluating this discrete Fourier transform? Okay, can you think of something here? Right, one thing that immediately comes to my mind at least is that we just explicitly evaluate all the terms involved in this summation. So knowing that k is equals to 0 until n minus 1, which is 3, or 0 means 0 until 3. So what I'm going to do is I'm just going to write all the different expressions for f0, f1 all the way until f3. So I have this now. f0 equals to f0e, then minus 2 pi I0, okay, 0 over 4. Well, this is going to take some time. Okay, let me jump straight ahead. Okay, so when we write everything explicitly, then this is what we have. Now, as you can see, we have 4 expressions, right? 4 equations expressions, whatever you want to call it, like F0, F1, F2, F3, and for every of these F terms, okay, we have to do this summation. So there is a 4 exponents to be calculated. Okay, in fact it is 4 complex exponents. So the example that we have right now is it is only for the case of 4 data points, which is not big. But when we have a bigger data, bigger data size, and in the order of many hundreds or thousands or something like that, then it's going to be lots of calculation, lots of computation, which is not good, right? So the idea now is, the drive now is to reduce the number of calculations. Can we reduce the number of multiplications, the number of exponents, exponential calculations that have to be done here? Okay. Alright, so we're going to look at that. Right, I have one idea on how we can reduce this calculation. Okay, if we look at these exponents, okay, now if we find the value for all these exponents, what will we get? Okay, so calculate all of this. Now, okay, how do we do this calculation? Okay, so this is exponent to the power of something. Okay, let's take a look at this, right? Okay, we have to make use of this particular identity, but before that, okay, let me erase this. Oh, it cannot be erased. Never mind. Okay, so we have to make use of this. Okay, okay, let's see. I something equals to cosine theta plus I sine theta. Okay, so this is Euler's identity. Now, so to calculate this exponent, we can make use of this. Okay? Then it will make it be easy. We have a complex number, and we can see the pattern when it comes to the cosine and the sine. Okay, the real part and the imaginary part of this complex number. I did the calculation using a spreadsheet program, OpenOffice calculator. Okay, and this is what I get. So I tabulate the value of a cosine, sines, but of course this is for a different example, an example that involves 8 data points, but it doesn't matter. What I'm trying to show here is the properties that I discovered. Okay, and I tabulated all these values. Okay, as I said earlier, the exponent we can calculate it as a complex number, cosine theta plus I sine theta. Now this is what I have. I can think of this as a matrix. Okay, now there are more values behind here, but never mind, I'll just explain what I can see here. Okay, so this matrix, it is symmetric in the sense that it is equals to its transpose. So you can see it here and here. Okay, so the matrix is equals to its transpose. Now surely we can use this, right, to come out with a faster discrete Fourier transform, to come out with a discrete Fourier transform calculation that involves less computation. So this might be an idea. Okay, there is another way to cut down on the number of calculations involved in computing the discrete Fourier transform, and this is something that we can arrive at if we know a bit about the properties of discrete Fourier transform. And of course, one can look up these properties in the Wikipedia page on discrete Fourier transform. And this is what we have. This is a snapshot of what I see. And especially interesting is this part here, the periodicity. Okay, so it says here that xk plus n is equals to xk. Well, can we take advantage of that? So this is the property that we want to take advantage of. Fk is in fact equals to Fk plus n. Well, how do we go about doing this? But the problem is that I have F0, F1, F2. Okay, in the examples that I showed you just now, I have until F3, is it not? Right. Now, what this says is that if I want to calculate, for example, what it means here is that f0 is equals to f0 plus 4 equals to 4, f1 equals to f5, f2 is equals to f6, right? So we have a problem here. We can potentially make use of this, but how? Okay, because what it means is this, right? And we don't have f4, we're not interested in f5, we are not interested in f6. We just want to calculate f0 until f3. How do we go about doing this? Maybe, okay, just maybe, we can do it in this way. So we have fk, right? Okay, we are interested in calculating this, is equals to, alright, okay, so we have this, right? 3n equals to 0, then fn e minus 2, where's my 2? Okay, 2, something wrong here. Okay, let me do it again. Okay, now minus 2 pi I and k over 4, right? Okay, so what if we split this summation nicely into 2? Okay, what I mean is this. Okay, so we have fk is equals to f0 e minus 2 pi I, okay, 0 k over 4, correct, plus f1 e minus 2 pi I 1 k over 4 plus f2 e minus 2 pi I 2k over 4, and finally f3 e minus 2 pi I 3k over 4. Now what if we split this nicely in this manner? Okay, because the idea here is this: if I can split it in this way, okay, somehow if I can split it into half, then maybe I can make use of the theorem that we saw just now, which is fk equals to fk plus n. So the idea is that we think of this as a Fourier transform by itself. We think of this and as another Fourier transform. We play around with the variables, and somehow we'll be able to make use of this. Interesting idea, but will it work here? Well, I cannot think of a change of variables that will allow me to write this as a Fourier transform, and this is another Fourier transform. Okay, let me try this. N equals to 0, and this is 1, correct? Half, 0 and 1. This is half of the original Fourier transform, and we have f, n, and then e minus 2 pi I. Okay, but it doesn't make sense. I cannot change this. I have no idea right now how to make this be a Fourier transform myself. This is not a discrete Fourier transform, because this is 4 and this summation is until 1. So this doesn't define a complete Fourier transform. And the same goes here. I have problem as well here, because this is n equals to 2 all the way until 3, right? And fn e minus 2 pi I n k over 4. So this is a double problem, because I'm starting from n equals to 2. No, it doesn't look like a proper Fourier transform, but it does seem attractive, right? The idea of splitting the Fourier transform into 2 and then treating each one of that as an independent Fourier transform, and then somehow we'll be able to make use of this. Well, okay, so we shall give another go at this. What if now we split the terms, right? The terms in the Fourier expansion, in the Fourier transform calculations. Now we split those terms into 2. Okay, we split specifically into the even and odd terms. Okay, so what it means here is this: Okay, we have f0, for example, okay, equals to f0 e and then minus 2 pi I 0 0 over 4 plus f1. Okay, go on and on. Okay, let me just write down the general form here. Okay, fk, if I want to split this fk into two, the even term and the odd term, so I can maybe do it this way. Okay, so now that I have split into two, now assume that it's okay, the number of terms is even, so it means that we can split them nicely. So then we have here n over 2, right? And this will be n equals to 0. Now f, okay, so I want to take only the even data value, so I have here 2n, correct? Because when n is equals to 0, then 2n equals to 0, and when n is equals to 1, then we have 2 times 1 equals to 2, which is an even number. Okay, so times e minus 2 pi I, right? And what do we have here? Okay, instead of nk over 4 or nk over n, okay, I'm using n here, right, instead of 4. Okay, never mind. Okay, so instead of nk over n, big letter n, we have here 2n, right? Because we just want the even number, 2nk over 4, right? So as you can see, this is the even part. Now let's look at the odd part. Last, okay, what do we have here? Now again, because we split the expression nicely into two, the even part and the odd part, so this shall be n over 2, correct? N equals to 0. And then we have f. Now for the even part, we have here 2n. Now for the odd part, okay, let's just do some common sense thinking. It should be 2n plus 1 is my guess, correct? No, when n equals to 0, we have 2n plus 1 equals to 1. When n equals to 1, we have 2n plus 1 equals to 3. Well, that seems to be right. Okay, now we have the exponent e, okay, minus 2 pi I, and then we have here 2n plus 1 k over 4, right? Okay, why am I using 4? Okay, I mean that was in the previous example. Okay, so it means that one moment, excuse me, and excuse me, so 4 divided by 2 is equals to 2. Alright, now where are we now? Okay, so this is the odd part, right? So what do we have here? We have something here. Okay, so now let's just play on. Okay, equals to summation 2n equals to 0, and then we have f 2n e minus 2 pi I. Okay, we have 2nk divided by 4, so we can simplify 2 and 4, right? So it means that we have nk over 2. Perfect. This is perfect, see? Because this looks like a Fourier transform by itself of size 2. Wonderful. Now let's continue. Last, okay, 2n equals to 0. Now f 2n plus 1 e. Okay, what do we have here? Minus 2 pi I. Okay, I'm going to split this part apart. Okay, so this will become 2nk over 4, and then we have another e minus 2 pi I, and then we have k over 4, right? Okay, so where are we now, and how do we progress from here? Okay, so we can certainly simplify this, so this becomes 2, and you can see the similarity here. I mean, it is exactly the same, right? So in other words, this part here is becoming like, you know, a Fourier transform by itself. We just need to factor this out. Okay, put this outside here. Okay, so what do we have? Writing it all back nicely. So this is what I have. Okay, as you can see, this is a Fourier transform. a discrete Fourier transform, and this is another discrete Fourier transform. This is the even part, and this is the odd part, correct? Alright, and this is a term which multiplies this summation. Okay, now what we have here is this. Okay, we can write it in this way. Okay, okay, I'm going to write the FK, yeah, okay, FK, right? So in other words, FK is equals to, no, it should not be O, E starts with, even starts with E, right? So why am I writing O there? Okay, so E, okay, the even part, plus E minus pi I K over 2 O K. Alright, this looks very nice. And okay, so this applies for K, this is a Fourier transform of size 2. Okay, what I'm referring to is this and this, right? So in other words, this K is K equals to 0 and 1, right? So what it means is that I need just to calculate EK for K equals to 0 and 1, and I should be able to get directly, okay, E2 and 3, and the same goes for this. Okay, so let me write this. E0 equals to E3, E1 equals to E0 equals to E2, E1 is equals to E3, and the same goes here. O0 equals to O2 and O1 equals to O3. Okay, so I can calculate these two terms in one go. Okay, if I know E0, I can get E2. If I know E1, I can get E3. Very simple. So it means that I'm doing less work to calculate FK. Okay. All right. So can you see something here? No. The main problem, the one thing that we have left now is this. Okay. What properties of this? Okay. What is the property for this? Okay. I don't have the reference right now, but can we infer something here? Okay. Can we have a shortcut? Okay. Is there some kind of an identity that will allow us not to have to calculate this all the time? Okay. Okay, we are interested to know how we can calculate this efficiently. Okay. Right. Okay, so specifically, okay, we want to know about this IK plus 2. Now remember, the size of our data now is 2. Okay. Right. Okay, what does it mean here? Okay, so now the 2 here. Okay, so we have to remember that we have Fourier transform EK and OK. They are of size 2, so that's why we have 2 there. Right. So how can we study this? Okay, so E minus pi I K over 2. Right. E minus pi I K, 2 over 2 is 1, so it's nothing. Alright, am I seeing something here? Okay, what is this part? Okay, what is this? Okay, what is this? This is that. But this, what does it mean? Okay, what is the meaning of E minus pi I? So we have cosine minus pi, Euler's identity. Okay, this is Euler's identity, and I really hope I pronounce his name correctly. Okay, so now we have this cosine minus pi plus I sine minus pi. Okay, what is cosine minus pi? Okay, cosine minus pi. Okay, let me plot the cosine curve. Okay, this is the negative part, right? Okay, so this is 0, and what is this part here? Okay, this is one circle. Okay, this is one cycle. Am I right? This is one cycle, so it means that this is 2 pi, and this is the pi, right? Okay, so what it means is that this is -1. Now what about the sign? Okay, so let me plot again using a different color. So we have something like this. Zoop, no, it doesn't go like that. This is the positive part, so the negative part will go like that. This, it looks interesting, right? So in other words, this part here is 0. So what we have here is e minus pi k plus 2 over 2 is equals to negative e minus pi I k over 2. Let me solve the I here. Okay, so this is the formula that we can use. Okay, so we don't have to calculate this all the time. Okay, we don't have to calculate this all the time because we know that this is true. I mean, we can make use of this sort of relation. Okay, so I hope I have shown the essence of the fast Fourier transform. It's all about trying to cut down the number of evaluations, the number of computations involved in the discrete Fourier transform, and we try to cut down on the number of calculations by using some properties of exponential, some properties of the Fourier, discrete Fourier transform. Okay, thank you, bye.